Welcome to video 2.2, Atomic Structure and Pre-Atomic Theory. Notice the word theory here. If you remember, a theory is what we believe to be true based upon what we know. And so in this video, we're going to start looking at the history, the origins of what we believe to be true about the atoms and how they exist and how matter. And we're going to look at that theory about how it's changed over time. And then in the next few videos, we'll actually see what we believe to be true today with our modern atomic theory. In this video, we're also going to touch on protons, neutrons, and electrons, the nucleus, and the experiments that helped us determine that they exist today. So here are a few vocab terms you're going to come across. A lot of this should be familiar. The new word quark might be in there. You might not have heard the Plum-Pudding Model or Dalton's atomic theory, but the rest of those words you probably should have heard already and you probably are familiar with from your middle school science classes. So as we get started, we have to go all the way back in time to about 350 BC. Around 350 BC to 300 BC were a couple famous Greek philosophers. One of those was Democritus. And the guy that Democritus had a different opinion was, a different viewpoint from, was a guy named Aristotle. Aristotle is somebody you've probably heard a bunch about. He's a famous guy, and Democritus you maybe haven't heard so much about. Well, Democritus and Aristotle had conflicting views about what matter was in life. So they both would use logic and reasoning, and they would try to explain life's great mysteries. In this time period, they did not do science projects. They did not do a lot of hands-on experiments because, one, they didn't have the tools or equipment to do it, but two, this was also a slave-based society where you were wealthy if you were able to work without your hands, and if you could use logic to show your intelligence. And so Democritus and Aristotle would have debates about life and the origins of matter. And so in that debate, Aristotle would say that all matter is able to be divided infinitely. He would say that think about matter like a number. If I take the number 2, and if I divide 2, I can divide in half into 1. If I divide 1 into half, it becomes a half. If I divide a half into half, it goes into a fourth. And if you keep dividing out, you would go into an eighth and a 16th and a 32nd. And essentially, like numbers, matter is always divisible. It will always continually be able to be divided up smaller and smaller and smaller parts until eternity. Well, Democritus had an opposite idea. But since Democritus wasn't as popular as Aristotle, Aristotle's idea ruled until about the 1800s. But for right now, we're going to look at what Democritus says, because what he said we believe to be true still today, for the most part. Democritus had this idea that matter was made up of something small, and that there was a small, indivisible thing that could not be split up anymore. So when you looked around and you saw a piece of matter, you could break it up, but eventually it would come to some small, what we would call a Lego block, some building block that could not be split up anymore. The word he used for this was atom, which literally means indivisible. And so again, Democritus' work was based upon logic and reasoning and not necessarily science. So enter into the equation of history Mr. John Dalton, 1808, roughly 2200 years to 2100 years after Democritus' idea, we started doing experiments. And Dalton was looking around at all this different information and data and experiments coming around, and he came up with his atomic theory. And he said a few things that we believe still to be true today. He determined that elements are only made up of atoms. And he used that word atoms going back to Democritus when he created that word, which meant indivisible. And that all these atoms could only combine in whole numbers to form what we call compounds. Meaning, we write a chemical compound as H2O, not H.5 and 0, 1. But really, it's that, let me say it again, not H1O and a half, but H2O, and not C.501, but C1H or O2. So the idea here is that these atoms have to combine in whole number ratios. So there were 5 things specifically that Dalton said to us about atomic theory. And these 5 major ideas are still mostly true today, even though they have slightly changed. At least one of them has slightly changed and became a better explanation. So his 5 ideas were that all matter is made up of atoms. Got it. Check. All matter is made up of this little particle that, although it's defined, its origins are the word indivisible, that we do accept that there's these things here, these little, and we represent by the circles here, these atoms that make up all matter in our world. And we believe that still today. We believe that atoms are elements of identical properties. So meaning that if I have a chunk of gold and a chunk of gold, those two behave the same. They behave chemically and physically the same because they both are made up of the same atom. So all atoms of a certain element have the same properties. He also believed that atoms could not be divided. This was like Democritus, that atoms could not be divided anymore. This part of the theory has slightly changed since, because in the last few years, we've actually identified these things called quarks. And quarks are what make up protons. And even an atom, we know, can be broken up into protons and neutrons and electrons. So the idea that an atom cannot be divided is partially true and partially not. It's not true because we know atoms are made up of protons, neutrons, and electrons. And we also now know that protons, neutrons, electrons are also made up of things called quarks. So you can go back to Aristotle and Democritus' debate again. Who was right? Well, we don't really know, but we do know that atoms exist. They're the smallest thing that retains its chemical properties. The other part of Dalton's atomic theory is that atoms make up compounds with whole number ratios. This simply says that we have things like CH4, not C.25H1. That whenever atoms come together, they are a whole unit, and when we combine them in a chemical, we have to show whole numbers in the subscripts. And the other thing Dalton says is that in chemical reactions, these atoms will get rearranged. They will either get separated, known as decomposition, they'll get combined, known as synthesis, or they'll get rearranged, which could be forms of combustion reactions, double or single displacement reactions, and double displacement reactions, which we'll learn down the road. So what is it that we understand today to be true? Well, we still understand the atom. We accept that the atom is the smallest particle of an element because it retains those chemical properties. I know I can split up an atom. I know I can split up the protons and neutrons. That's called nuclear chemistry, which we'll get to at the end of this unit. But for right now, we see this to be true, that this guy exists as protons, neutrons, and electrons, and that specific combination of those subatomic particles come together to make a certain atom with certain chemical properties. What else do we now know to be true? We also know that the atom is made of protons, neutrons, and electrons. These smaller particles are found in different locations. First, we have the nucleus, where the protons and neutrons are located. And then on the outside, you'll hear things like the electron shell, the electron cloud, or the electron ring. It all is used to explain the same idea that these electrons are moving rapidly around the center of a nucleus. And then we also have even learned recently in science and chemistry that these subatomic particles are made up of things called quarks. And we know now there are 6 quarks, and we've even identified and labeled those 6 quarks, but that's getting a little bit too deep for Chemistry 1. But pretty cool stuff. So what else do we see here? Well, we also see that these protons and neutrons exist in the nucleus. And in that nucleus, they are held together by what's called the strong nuclear force. And we have these things called neutrons in there, which have no charge, but they act as a buffer. They act as something to allow this electrostatic repulsion so that we can have a balance between the nuclear force of the neutrons and protons holding together, but yet not allow these protons to push each other apart so that the nucleus would not dissolve. So we have nuclear forces, again, both the strong nuclear force, which is also electrostatic repulsions, that holds these protons and neutrons together in the nucleus. So now, what were the experiments? We're going to look at 2 major experiments that have helped us understand and to discover the electron and the nucleus. The first experiment we see here is called the Cathode Ray Tube. This Cathode Ray Tube was a simple idea. Basically, all this is a neon light. When we go out downtown and we see stores that have neon lights, they do it to get our attention because they're bright and they're beautiful and they're colorful. Well, the Cathode Ray Tube was the same idea. It was a tube filled with different noble gases. So these cathode ray tubes would have different noble gases in there, and that's where the idea of neon lights came from, because that's a certain form of a cathode ray tube with neon gas in there and electricity passing through it. But what happened is these glass tubes had gas inside. And when you hooked up an electrical current that came from the cathode to the anode, we actually saw a beam of light that stretched from here to here. So somehow, in this glass tube that did not have anything in it that conducted electricity, there was a way for this beam of light, this laser-looking thing, to go from one side to the other side. We determined that those things are probably going to be a negatively charged particle because we hooked up a magnet to it. And so you hooked up a magnet, and I'll show you a video of this in class of a guy actually doing this, that we saw that light, that laser, begin to bend, to begin to get attracted to that magnet, which determined that whatever this stream was going across had a negative charge. And so he determined that the small beam is made up of something smaller than an atom, and he had calculated it to be actually 1,837 times smaller than the mass of a hydrogen atom, which was the smallest atom known. And these guys are eventually what we call electrons. So the big idea here is that the cathode ray tube discovered the electron by passing current through a glass tube, seeing a beam of light or a laser looking thing, and then pulling that laser away with a magnet, which determined there's a small particle called an electron. Now, one of the models we have is called the Plum-Pudding Model, and this is going to be important because it's going to be disproven in our next experiment called the gold foil experiment. So the Plum-Pudding Model was an idea of how atoms were arranged. We know atoms are made of protons, neutrons, and electrons, and at the time, they believed in 1904 that plum pudding was the way an atom was made. So basically, you had this overall positive experience with just negative particles from the cathode ray tube distributed throughout this thing, through this space. So think of it like plum pudding, or we don't eat plum pudding, but think of it like banana pudding, or any kind of like tapioca pudding, where there's this pudding, there's this mixture, there's this gel with different floating particles inside that gel. And so the idea was that the positive and negative charges were all distributed evenly, that the gel was positive, but then there was these little particles and there's these little chunks of either bananas or cookies or tapioca balls that held these negative charges. So Ernest Rutherford came along and he designed an experiment. And in this experiment, he took alpha particles, which is nothing more than fancy helium atom. So a helium atom is going to be 2 protons with 2 neutrons. An alpha particle are just the protons and the neutrons without the electrons. And so he shot these helium particles, or these alpha particles, through a piece of gold foil. So when we say gold foil, think of aluminum foil. And when he shot them through there, because of the Plum-Pudding Model, he expected those particles to go through there like a cannonball going through tissue paper, is what he said. So he expected these alpha particles to just blast through the gold foil and nothing special would happen. But what he saw here when he did it, and I have an illustration here, was a little bit different. So what we see here is a lead block, and we're shooting off alpha particles, which is just really helium atoms without the electrons, through the gold foil, and then there was a screen around it that just detected the landing of those alpha particles. And what he expected was this. He predicted that this cannonball-like 4 times the size of these electrons would just tear through that and go through in a straight line. But as he expected that beam to go through without being influenced, here's what he actually saw. He shot those alpha particles through, but again, 1 in every 8,000 got deflected. And so what happens here is that most of the particles did go through. But again, 1 in about every 8,000 bounced back, and some of them completely reversed their path. So there had to be something in there. Every now and then there had to be some solid unit that these guys were ricocheting off of or bouncing off of. So again, we see that the gold foil experiment proves plum pudding is wrong, because the atom is mostly empty space, but there's this small, dense, positive nucleus, and that when the alpha particles got close to it, it either bounced back or got deflected. Now, how do we know this dense nucleus was positive? Because of what we shot. We shot alpha particles, which were, again, helium atoms minus the electrons. So if they're missing their electrons, they have a positive charge. And so as a positive charge came in, it either got reflected or it got deflected off this other positive charge. And so as we come through the conclusion of this, again, we see that atoms must have a dense area with a positive charge. And this we call now the nucleus. And so Ernest Rutherford's gold foil experiment discovered the nucleus. So again, if you haven't watched the whole video, here's the big idea. This is all a theory. This is all what we believe to be true. This has been changing since 350 BC up to about 1908, and even today it's still changing slightly. But scientists and chemistry have proven that there is an atom. An atom is this idea of the smallest unit of matter that still has the same chemical properties. And all these scientists keep building and adding on each other, but the idea is still true. The atom is there, and it contains the protons, it contains the neutrons, and it contains electrons. The neutrons and protons are in the nucleus, which is a dense, positively charged center, and the electrons move freely around in things like called the electron cloud, the electron shell, or in electron orbitals. Have a great day.